Today what we're going to do is talk a little bit about going even deeper down to the physics of what's going on inside of a computer. Today what we're going to do is talk a little bit about going even deeper down to the physics of what's going on inside of a computer. And I've broken this topic up into two topics, one having to do with communication and one having to do with computation. So today we're going to talk about getting the bits from here to there, and in the next lecture we'll talk about actually doing computation, the ands and the ors and the nots and stuff like that. But we're going to talk about some of the fundamental issues. Now, usually at MIT when I teach this class, the students have had beforehand a course in physics and a course in circuits. And so you're going to see in the notes here some mathematics about how to quantitatively figure out some of the issues here. I'm going to gloss over them a little bit this time. We're going to do sort of, what do they call it, physics for music majors or something? I don't know exactly how it goes. But anyway, physics for poets. However, Sam's son is going to come in here, and hopefully we'll be able to give you a slightly deeper notion of how some of these things work. Okay? But at least qualitatively, you'll be able to understand what the issues are and how they work. And that way, that actually helps you in learning some of the quantitative stuff. So you remember from our last lecture that we had this thing called the static discipline, and that the idea of the static discipline was that we were going to accept voltage signals of lesser quality than we transmit. And so if every gate obeyed this static discipline, then we could afford for these high-quality outputs to be contaminated by some noise before they reached the receiver at the next gate, because that next gate was not so picky about how good the signal needed to be. That's fine in terms of how to actually transmit the bit, but let's go a little bit deeper and ask our questions about what is a bit to begin with. Okay, what is a 1, what is a 0? And this first question is, what is this information about anyway? And so, the person I put up here, everybody knows who this is, right? Mr. Holmes, right? Anybody who knows who this is? Conan Doyle. That's absolutely right. Conan Doyle, who wrote the Sherlock Holmes stories. Oh, really? That I did not know.
What?
A failed physician. He was a failed physician.
But he patterned Sherlock Holmes after one of his internal medicine lecturers, who would bring a patient into the room,
yes,
say absolutely nothing, and have the patient out, and ask the class what they had observed.
And then by process of deduction, figure things out. Well, in all of those stories, there are these clues, right? And the clues help you to zero in on who did it. And the clues are not total information about who did it, but each one sort of brings you closer and closer and helps you to lower your uncertainty about who may have done it. And so the important thing to realize about information is that it is something that sort of lowers your uncertainty about what the answer is. So as an example, if I toss a coin and I tell you whether it's heads or tails, I've given you some information. And that amount of information telling you what the certainty of one thing out of two equally likely possibilities is the actual definition of one bit, of one binary digit. It was either a 0 or a 1. Now, if we toss 3 coins, we have an intuitive understanding that that should be 3 bits of information, because after all, the 3 coin tosses are independent of each other. And so each one is equally likely to be a 0 or a 1. Another way of thinking about this is that there are 2 to the n, in this case n is 3, or 8 possible ways to toss 3 coins, right? You can do head, 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 tail, etc., and there's 8 different combinations. And by telling you all 3 coin tosses, I'm picking 1 out of the 8 of the equally likely possible 3-way coin tosses. Now, how you measure information in general amongst equally likely possibilities, this is just what I wrote up on the board, that if the number of bits is n, the number of possibilities is 2 to the n. The way in general that we measure information is we take a look at how much is resolved by telling you what happened here. Now, it's not necessarily the case in coin tosses, or apparently in politics either, that choices are equally likely, okay? And in particular, let's think a little bit about crooked coins. So what if the probability of a tail, instead of being 0.5, was 0.25, and the probability of a head was 0.75? And I flip a coin like this, and I tell you whether it's heads or tails. Do you think that I have given you as much information as I did if the coin toss was 50-50? In other words, if it was not a crooked coin. Most people are saying no. Okay? Well, I think that you can convince yourself it's true by weighting the coin even more and making the coin so crooked that it always comes out heads. In other words, P sub tail, the probability of a tail is 0, and the probability of a head is 1. And I flip the coin, and I say, guess what? It's heads. Have I told you anything that you didn't already know? The answer is no. And so we might expect that if I were to draw a chart of sort of how much information, this is the amount of information, versus what the probability of a head is for a single coin toss, that the curve would kind of look something like this. Now, we don't know exactly what it looks like yet, but we know that if the probability of a head is 0.5, that we get 1 bit of information. And we know that if the probability of getting a head is 1, we get 0 bits. Because when I flip a coin that's always going to be heads, and I tell you, guess what, it's heads, it's 0. But somewhere in the middle, when the probability, let's say, is 0.75, like it is up there, we would expect the information to be somewhere between 1 bit and 0 bits. And the question is, how much information am I really telling you? So back in the 1940s, there was a guy named Claude Shannon who pioneered the study of this information theory and came up with a very nice formula for measuring how much information there is in a crooked coin toss like this. And here's how it goes. The first thing that you do is you take all of the probabilities of the different events taking place, whether there's 8 of them or 2 of them. So in this case, there are 2 of them because we only have 1 coin toss, and I is, let's say, either 0 or 1. And so one of the probabilities, let's say P sub 0, would be 0.25, and the other probability would be 0.75. Okay, that would be P sub 1. And you take the log of the probability base 2. Now, why should you do that? Well, let's go back to our example of the 3 coins, and remember that there's, 8 possibilities, right? And each one of them is equally likely, and the probability of having one of these triplets is exactly 1 over 8. Okay, well, what's the log base 2 of 1/8? Log base 2 of 1/8 is -3. Ah, so this looks interesting because, of course, it sort of makes sense, right? Because the log base 2 of 8 is 3. And for those of you that don't know it, the log of 1 over something whose log is 3 is -3. Okay? So -3. So this is the probability here is equal to P sub I. So -3. That's how many bits I tell you, except the sign's wrong. So we have to change this to a +3, so we'll put a minus sign in front of it. So that's how many bits that I would tell you if I picked one of these things that were equally likely. Except that in this case, certain things are more likely than others. Heads are more likely than tails. So what I want to do is say, well, it's not the case that they're all equally likely. What I want to do is, instead of taking log base 2 of P sub I, is I want to form what's called a weighted sum. In other words, I want to find out what is the average number of bits over all the possible combinations. So what we just said is that the number of bits that you would transmit if you said 0, 0, 1, and each was equally likely is 3 bits. And the number of bits here is 3 bits, and the number of bits if I told you this is 3 bits, and the number of bits if I told you that is 3 bits. And so the average of all these 3's is 3. That's the average amount of information I tell you. In a similar way, if I have a single bit, a 0 or a 1, well, what's the probability? P of 0 is 1/2. P of 1 is 1/2. The minus log base 2 of 1/2 is equal to what? 1. Okay, so this is 1 bit of information if I tell you 0, and it's 1 bit of information if I tell you 1. What's the average number of bits? 1, okay, in either case. But now we're ready to say, well, what if it's not equally likely? The same formula works, except that I need to sort of do a weighted sum. So if the probability here, instead of being 1/2, is 0.75, and the probability here, instead of being 1/2, is 0.25, then when I take the log base 2 of 0.75, can anybody do that? Do you have a calculator? I guess I could do it here, right? Do we have? I think we have log, right? Program. See if Microsoft gives us log here. Calculator.
You have to turn on scientific functions here.
View scientific. All right. You ready? 0.25. Now we have natural log, right? ln here. So but that's not quite right. So how do we do log base 2? Anybody know? I think Sam has gone to get his calculator. Okay, so we do that and then do what? Divide by the natural log of 2. Divided by 2 natural log equals -2. Now, why does that make sense? Because 0.25 is 1/4, and the log base 2 of a quarter is going to be 2. Right? Okay. So that's -2. So this is 2 bits of information. Now that's interesting, isn't it? This means that if I tell you that this thing came up, in this case, tails, right? Is tails the less likely one? I think that's right. Then I have sent you, so he's all ready to go. I have sent you, so Bill Gates beat you by a few seconds, but only for one of them. So you get to do the second one. If I tell you, if I flip a coin that's more likely to come up heads, and I say, guess what, it came up tails, are you more surprised or less surprised? What if I were to tell you now, guess what, it turns out that the court has changed its mind and Gore wins? Have I given you more information than if I tell you, guess what, Bush wins? That's less information. So it makes sense that the less likely something is to happen, the more information telling you that it happened is. Okay?
Can you elaborate on the logic behind that?
Sure. If I give you verification of a likely event, I have not lowered your uncertainty about the event very much. But if I tell you that a very unlikely event happened, then your uncertainty has changed a lot. Okay? You were not at all sure that it was going to happen. I'm not at all sure that Gore has a snowball's chance, as they say, right? And if somebody were to tell me that, it would be like, wow, I got lots of bits just then. Okay? So you have to understand that a bit is not just a choice between two things. A bit is a choice between two equally likely things. And the less likely something is to happen, when you learn about it, the more bits of information you have learned. So it was just defined that that information that gives you the outcome of two equally likely events is going to be defined as 1 bit. Once you've decided on that as being sort of the base that you will operate under, then, of course, if you want to measure something that doesn't have a equal power of 2 sort of thing to it, then you may be tempted to use a different base. I could, for instance, have said a choice of 1 of 3 equally likely things is going to be 1, trit, okay? And that would be a base 3 type of thing to do.
I just don't understand why logarithm at all comes in.
Oh, why is it that the logarithm? It has the characteristic. Let me see if I can explain this well. It has the characteristic that if I have two independent events, and I tell you information about one, and I tell you information about the second one, that the sum of the information that I tell you is equal to the number of bits that I told you about the first one plus the number of bits I told you about the second one. It tends to be the case. So let's say if I had n events here, and I have m events here, okay? And I tell you a certain number of bits. I tell you small n bits by picking one of these choices, however I do it, and however likely they are. And I tell you m bits by picking one of these choices. And these two picks are independent of each other. It is definitely the case that the number of possible pairs I could do is n times n, right? So that's the number of total choices that I could make. So if I were to draw out all n times m of them and pick one of those, that's equivalent to picking one of these and picking one of those. It must be the case that the measure of information for 1 out of n times m is equal to the measure of information for this plus the measure of information for that, which is the reason the log is used, because when you take the log of a product, you get the log of this plus the log of that. So the amount of information of choosing 1 of n plus the amount of information of choosing 1 of m. And that's why you're stuck with the log. It could have been something different, but the log happens to have this property, which is what I think the reason is that we use it.
Unit for information?
There's just a bit. A bit? No, that's it. 1 bit, as far as I know. Okay. Yeah.
So if you have more bits of information for probability that's less than half, what does that mean for this curve that you draw on the right side of the board?
Well, what I've drawn here is what the average probability is going to be. Okay, the average. So I toss a coin and I tell you something. Okay. Now what I just did over here was a little different. I tossed the coin. I hypothesized that I'm going to tell you something rare, which is going to be 2. You know, the fact that it's going to come up tails. Now let's take a look at what happens if it comes up heads. What's the log, Sam, base 2, of 0.75, of 3/4? Okay, 0.41 bits. So it's less than 1 bit if I tell you something that is likely to happen. Okay, that's good. But what's the average amount of information if I toss a crooked coin like that? Well, you may be tempted to just average 2 and 0.41, to add them up and divide by 2, but that would be wrong. And the reason it would be wrong is that this one is 3/4 is more time, is 3/4 likely to happen, and this is 1/4 likely to happen. So this will happen 3 times more often than that one. So what we need to do is we need to weight the average and say that we multiply this by 0.75, multiply this by 0.25, and add them up. Okay? So what you get when you do that, and take the weighted average of these two things, 0.75 times 0.41 plus 0.25 times 2 equals 0.8075, or 0.81 bits. Yes, and that is exactly what we just did down here. So on average, over these coin tosses of a crooked coin, let me clear this thing out now. All right, now this takes real skill here to operate the mouse upside down. Okay, on average, the number of bits that you'll get from a crooked coin toss is 0.81 if the probabilities are like that. And so what we've seen is that looking down this curve, that this is 0.81 bits. So this is average information. Okay. However, when the unlikely event happens, we send a lot of data. Okay, a lot of information. Okay, what if, and I actually already told you this thing, what if we keep just saying, Bush won, Bush won, Bush won, I'm so depressed, Bush won, Bush won, Bush won, Bush won. Have I told you anything that you don't know? The answer is no, okay? And this is important to realize, that information is not a measure of how many zeros there are. Okay, it's a measure of how many zeros there are only if each zero that you get, it was just as likely to get a 1. But if you know beforehand that it was going to be a 0, on average there's no information. Now you may say that there is some information at the beginning, maybe 1 bit, saying whether it's going to be all zeros or all 1s. But certainly on average the amount of information is 0. How about here? What if you have 1s and 0s back and forth? What if I came here and I gave exactly the lecture I gave yesterday? What if we set up a robot that played the tape that I did yesterday and did everything exactly the same? Is there any information that you'd be getting, any uncertainty in your mind that would be resolved by listening to that tape? Well, maybe there is. Well, okay, let's assume that you guys learned perfectly the first time around. Is it resolving any uncertainty hearing what I'm going to say? The answer is no, because you've heard it before, right? And in general, if there is a capacity to predict the next bit based on the previous bits that you know, even if the pattern is not constant, the number of bits of information is 0. Okay? Cool.
I guess you are arguing again there's really 2 bits of information.
Maybe there's a bit saying, you know, whether you started off with a 0 or you started off with a 1, things like that. But let's say that you actually knew what the pattern was going to be. In that case, there's actually 0. And certainly on average, and by what I mean on average is the number of bits of information divided by how many symbols you got, how many zeros or 1s you got, will go towards 0. Okay. It's not useful to keep saying the same thing over and over again, no matter how complex the thing is.
Wouldn't you have to know that the bits are somehow signal rather than noise?
Well, that's a good question, because in general, there's this confusion that happens all the time between how many bits of information are there and what is the meaning of the bits, right? So, for instance, I could give a lecture here, okay, and it could feel like a really great, brand new lecture that you were getting, but the truth is that if you took my class at MIT before, you'd be bored. And so, to some extent, it does depend on the receiver, whether the receiver has a predictor on the inside. Now, of course, the lecture is not exactly the same, but the amount of information somebody who saw my course before would receive from me giving it again is less than you get hearing it for the first time. So you are right. But in general, when you're talking about these things, we usually, you know, except for very crude models, we assume that the receiver does not know, in fact, what is going to happen. Okay.
I was thinking of it more from the sender end, that you knew that
Okay.
this was being encoded to mean something rather than just random. Because
Well,
by the predicted definition, the random
Sure.
thing would work out to be
It,
enormous amount of information.
it actually becomes very difficult to talk about that and to discern the difference between data and noise, okay? And we're actually going to get to that in just a few slides. So why don't you hold off, and then if you still have a question. It's actually a very deep issue. Let's talk about English, okay? So this is the one I give at MIT. I could have changed it for this class, but I didn't. But what does this say, this first thing? So I'll give you a hint. The first one is 6004, okay? With smart students. Great. Why were you able to do that? That's kind of weird, isn't it? That we can do that. Well, if you think about our definition of information, and we say, well, let's say that every English letter has maximum uncertainty. What that means is that the letters have an equal likelihood of happening, and furthermore, the assumption that we've been making with these coin tosses is that they're independent of each other. Okay, now both of these assumptions for letters are wrong, but if it was the case that that was true, and there are 26 letters in the alphabet, then the average amount of information would be the log base 2 of 26, right? And how large is that? Sam?
It's 4.5.
4.5, okay, because 2 to the 4 is 16 and 2 to the 5 is 32, so somewhere between 4 and 5. But the actual truth is if I know the previous 8 characters of a typical English piece of text, the next character has an uncertainty of only 2 bits, not of 4.5 bits. Only one choice out of 4. There's really, you know, that much information that's being sent. And furthermore, if you use more information, so for instance, is it a noun or a verb? Or what kind of a text is this? It actually gets down to 1 bit per character. Now, what does this allow certain... What does that mean? That means that we have the capability, even if some of the characters are wrong, of reconstructing it. And the reason that we have the capability of doing it is that there is not log base 2 26 or 4.5 bits of information in each character here, because if there was, then there would be no way for us to pull things back. There is redundancy here. Okay, there is sort of wasting of the encoding of the data in a sentence like this. And English is full of redundancies like this. And the truth is that each character, each additional character of a piece of text is really representing only about 1 bit of information, even though there are 26 choices. The amount of surprise you have finding out that a word that says C-O-U-R-S, that the next letter is E, the surprise you have in seeing that is next to nil. Okay, now the surprise you have that this letter is a W is relatively high, but that the next letter is a vowel is pretty low, because you know it probably is. So because there's so much redundancy in the English language, the amount of uncertainty that's resolved by every letter is a lot less than 4.5 bits. In fact, it turns out to be around 1 bit.
But you're assuming for the second letter in that wish word
Yes.
that we know definitely that the first letter is accurate.
Well, we actually don't. So in fact, we look ahead a little bit for some of these things. Let's see, it's like here, we don't know that the V is accurate. And so we go forward and we say, oh, well, this must be a W. So our eyes are very good and our brains are very good at doing a pattern match of the whole word and being able to figure out that this was probably a W and not a V. And the reason is that the later letters give us information about what was probably in the first one.
But you're constantly assuming that there's a strong probability that each letter is accurate. If you had...
We are assuming that in general these are accurate, right? That the noise level is not too great. Okay, now if I told you that this was underwater and in a fire, maybe you wouldn't be so quick. But I think even then you'd still try to look at it, right? And try to find out whether or not how to sort of fix this thing.
We assume the patterns that we recognize are accurate,
Right.
and then what's not part of those patterns.
And also we sort of assume that the amount of noise isn't too great. That we're not going to, like when we look at clouds, right? I guess I could start to sing, but I'm not going to. When we look at clouds, we see shapes of animals, right? Or we see all kinds of things, and you can learn a lot about somebody by what they see, right? But the clouds are not really data, they're just noise. And so we're sort of assuming that this is not like clouds, that this is actually mostly data with a little bit of noise mixed in. Now, what does this allow us to do? How many people have heard of the program Zip or PKZip? Has everybody heard of those things, right? So what does it do? Anybody want to say what it does?
Removes some of this redundancy.
Yeah, it compresses a file. You can put English text in here, okay, and if a file is 1 megabyte long, how big will it be after it goes through Zip?
About 200K.
200K. So it reduces things by a factor of 5x here.
Is it software?
It's software. And what it does is it goes through the text and it builds a dictionary of likely mappings between the letters and reduces it to a file that if I look at the zip file, what does it look like? It looks like noise. It seems that every bit of this file is as equally likely to be a 1 as it is to be a 0. And if I were to play this file through a speaker, it would sound like noise, like shh, just like white noise. Okay. And in general, it's sort of a remarkable result. A stream of data, here's what Zip does. Okay, it takes lots of redundant bits, strips some of them off, creates fewer redundant bits, and has an inverse process that goes the other way. But the remarkable fact is that a bit stream which has sort of the most amount of information packed into it, where every bit is truly one bit of information. And here I need to be careful about how I talk. There's one bit of data transmission where I say I send you a 1 or I send you a 0. And then there's how many bits of information do I send you? And that's different, okay? I can send you a stream of all zeros, and I can send you many bits of data. But because the data is completely predictable, I'm sending you 0 bits of information. The units are the same, but one's kind of bits of data that I send you. The other one is bits of information. If I send you a stream of data that has the maximum amount of information, in other words, 1 bit of information for every bit of data that I send, what would you expect the bits to be like? Each one would have a 50% chance of being a 0 or a 1, and they would be independent of each other. So it would sound like a random stream of zeros and ones. And when you play that through a speaker, which, when you ever get the chance, you should do it, it just sounds like shh. And so here's something even more wild to think about. You guys have probably heard about the search for
SETI.
extraterrestrials, and SETI. And we are listening to the spectrum out there, trying to see if we can find life out there. Well, it's kind of a funny race. It turns out that the planet Earth, back in the 1940s and 1950s and 1960s even, used to emit signals that were very easy to detect as compared to noise. Because if you take a station that's doing AM, most of it is a carrier wave that looks like this. And a little bit, the carrier changes its height, amplitude modulation. Okay, so a little bit like this, a little bit like that, but pretty much looks like that. Okay? If you take my spread spectrum phone, wherever it is, and you were to listen and watch the stuff that comes out of there, it sort of looks, like this. It's random. Why? Because that spread spectrum phone is trying to compress the data as much as it can into the airwaves to fit as many phone calls as we can into a given spectrum. And the unfortunate thing about this is that the little green men that are up there are going to have a harder and harder time as technology gets better and better and signals start to look more and more like this. Because pretty soon, the radio signals that we send out are all going to look like this. And it's going to just sound like noise, random noise, even though we're sending data to each other. Because that's the optimal use of the spectrum. And so one of the problems that the SETI guys think about, and they don't have an answer for this, is that if the civilization we're trying to listen to is smart enough, we can't hear them. Because we can't tell the difference between the sun that they're near, which puts out noise, and the civilization, which is putting out stuff that looks like noise, but is actually optimal data that has 1 bit of information per bit of data that is being sent. Now, wait just a second. If you guys listen on the phone, how many of you have by accident picked up a phone while a fax is on? You ever done that? Okay. If it's an old fax, a 2400 baud or something like that, and you listen to it, it sounds like tones, like that kind of sound, okay? There it's modulating the frequency, so it's changing, what the distance is of the waveforms here as opposed to the amplitude. But that turns out to be a very inefficient use of the spectrum. How many of the rest of you have ever listened when a 56K modem is on the line and you pick up the line by accident? What's that sound like? Sounds like static. And that's why. Because the 56K modem is packing into the spectrum of the phone line, which is roughly from 300 hertz to 3 kilohertz, which is a very small spectrum to deal with. It's trying to pack in as many bits as it can. And it's actually as many as you can actually do, is 56K. And as a result, what you hear sounds just like noise. And you can't tell the difference. You can't tell the difference. Anyway, there was a question. Yeah?
So if you're given a string of zeros and ones, is there any way of looking at it and quantifying whether it just got some kind of pattern to it or not? For example, here you can hear to the sound and kind of say there's some pattern to the sound if it's musical, otherwise it's...
What the trouble is that it depends on the receiver and it depends on the transmitter. The transmitter and the receiver have agreed upon a code to use, and they send the code. If you are listening to a conversation in a language you don't know, it may sound like noise, okay? In fact, I'm trying to think of The language is, where the heck is it? Is it the Bushmen or something that have the kind of clicks, right? To us, it just sounds like noise, right? And all the clicks sound the same, right? Which is kind of the typical thing if your ear is in tune to it, right? And so really, it really depends on something that ahead of time the receiver and the transmitter have set up in order to base the conversation on. And unless you know the code, there's no way for you to just listen to the data and to know. And the more sophisticated, the better you use the channel that you're sending the data on, the more it sounds like white noise. So speech, text like that we write, is actually a very inefficient use of the spectrum, except as we're going to talk about in a second, and I've hinted at before, it allows for noise to come in. Yeah?
The SETI argument, that makes sense, and it also makes sense that it would be silly for them to be looking for straight analog signals. But even if they were looking for analog signals, it would be kind of ridiculous for them to look for analog signals that would be familiar to us, like 1950s TV style. Like,
Sure.
But even with a digital signal, there's always like telemetry establishment and handshaking, and all of those things are based on tight periodicity.
That
And
is
you're supposed
only
to
the case.
code
Okay.
handshakes when you receive a call.
Yeah.
It does a timing.
So when it first starts up, when a modem first starts up, it goes, right? And then there's a little bit of singing back and forth. But see, I was going to sing. There's a little bit of singing back and forth where these things sing to each other, and then they decide to go to the higher thing. The truth of the matter is that the singing, by and large, is to allow it to connect with a modem that's older that uses this stuff, okay? There's no reason that if you knew you were only going to use the white noise thing, that you couldn't just start out by saying, hi there, and then just have you try to pick it up, okay? And in fact, to the extent that we use a simple signal like this to try to start off, it's only because the engineers like to think in simple terms and say, okay, I'll use something dumb to start off with, and then after a few seconds are passed, and when it really counts, I'll switch over to the harder thing, which is to figure out how to deal with this white noise signal.
That's also a dedicated line. If there's any kind of a broadcast system, though, there would always have to be some kind of handshaking to establish like one communicator from it.
It's actually, that's actually not true.
Really?
If you read about spread spectrum, okay, read up on direct sequence spread spectrum modulation. Okay, if you're excited about this stuff, you'll find out that in fact, as long as the receiver and the transmitter agree on the code, okay, and of course, you know, why is one white noise to one person and data to the other? And the answer is that if you and I agree on the code, then I can just begin to transmit, and you can synchronize to where you are in the code without me having to send anything else, okay? You try to sync up. If it doesn't work, you sort of slip one bit. You try again and slip a little bit. And there's all kinds of methods for doing it without having to go back to this stuff. So, but it turns out there is a good reason that you and I do not speak as efficiently as we can. And here's the reason. The reason is that if I put in redundancy to begin with in my language, then you can tolerate a little bit of noise. And this is different than the analog noise I was talking about in the last lecture, where a very simple receiver could just say anything that's higher than the input thresholds or lower than the input threshold is going to be either a 0 or a 1. That's one form of tolerating noise. But in general, if I have an original message that is encoded as efficiently as possible, I can go ahead and put it into an encoder, and I can add redundant bits to it. I can add extra bits, which will allow some of the bits to get clobbered by noise, and then the corrector will take that stream, remove the extra bits that were screwed up by noise, and give me back the original message perfectly, okay? And there's a whole science to how to design those two things. A very simple one you might want to think about is take every bit that you get in and replicate it. For every bit you get in, send 2 bits out. Okay, it turns out that's kind of an inefficient one, but what if you do it every bit you get in, send 3 bits out? That way, if any one of them dies, you can look at the other 2 and just take a majority of every 3 bits, to determine the 1 bit that gets out. And so you can build a system, a very inefficient one, it turns out, that just multiplies the number of bits that come in by 3 and can withstand up to any one of those bits being bashed, as long as you don't bash 2 in a row or 3 in a row, as long as you skip 2 before you hit the next one. And in general, the modems that we use, the cell phones that we use, the laser discs that we use, a CD and things like that have all sorts of redundancy that is put into the bit stream in order to allow correction to be done for bits that are found in error. Some of you may have heard about something called ECC when you buy RAM chips, okay, for your PC. And you'll notice that the price for an ECC chip is in general around 20% more than it is for the plain RAM. So typically when you buy some DRAM for your machine, you have 2 choices. You have a choice of no ECC or ECC. And in general, the ECC one costs around 20% more than the non-ECC. ECC stands for error correcting code. And in general, for every, I forget how many bits, but this has around 20% more bits in it than this does. And whenever a word is stored into a memory like this, it computes a error correction code and adds 20% more bits. And that allows any single one of those bits to go bad. And then the reader looks at that and says, aha, I know that this one is bad, so I'll fix it. And then it gives you the right data out. Exactly as when we just read the sentence that was up on the board, even though some of the letters were wrong, we were able to fix them because of the redundancy of the English language.
How does it do it with such slight redundancy? I mean,
That's an excellent question.
It's like at 64, we do 72 instead of 64.
Let me see if I have the, here. So if you want to find out about this, so Sam, you asked me for more books here and stuff, read this book, okay? This is an excellent, excellent book on this stuff. It's fairly easy by a fellow named Hamming and talks all about that. If you want to learn more about information in general, I would take a look at this. This is very old. It was first done in 1949. But let me go back. This was just to answer that question. Okay, so now we're kind of learning a little bit about what a bit of information is and this business of what the effective redundancy is, stuff like that. Now I want to talk about this decision that we made, again, digging deep into why it was that we chose to kind of have the static discipline with 2 zones, one for a 0 and one for a 1, and how we established this business of the VIL and the VOL and things like that. And so I have this great story that I like to tell, which is that the little green men that the guys from SETI are looking for, they actually came to Earth one day, okay? And they decided that it's time to go back, but they want to take with them the all the knowledge that we have on Earth. And so they go to the Library of Congress. They forget about the newspaper from the last day or two because they don't want to know about that stuff. But this is what they do. They say, okay, let's say that there are, I don't know, we said that there's how many bits is 1 character out of 26? 4.5, right? Well, 4.7 bits. So let's say that they use 5 bits to represent a letter, A through Z, and numbers and things like that. And they say, okay, here's 5 bits, okay? Let's say that's the letter A. I'm just making this up, okay? So actually, let's make it the letter I. I, and here's the letter T, and here's a space, and so it's it, space, and then the letter W, and it was a dark and stormy night, okay? And they just start putting all these bits down over and over and over again. And they do this for every book in the Library of Congress until they have a single bit stream, which is very, very long, okay? You know, they're very smart green men. Okay, they work fast. Now they take this bit stream with millions of bits, and say, you know what? That is a finite amount of information. In fact, that is a number. So there's a very long bit stream, okay? But here's the end of it, and here's the end of it here. That's a number. That's a number between a bit stream with all zeros in it and a bit stream with all ones in it, okay? And if I think about this number as representing a fraction, in other words, this corresponds to 1, and maybe, 1 with all zeros corresponds to 0.5, and this corresponds to 0, I can think of any bit stream, no matter how long the finite length is between 0 and 1, as representing a fractional number between 0 and 1. So, this is, 0.7071325, I figure out what that is. And since I'm a little green man, I am going to take this bar of material called impervium, okay, well-known stuff, and I'm going to scratch a line in this bar. And that line will have a distance from this end compared to the distance on the hole, where this distance is the fraction of the hole that my data is right there. So this will be, I didn't quite draw it right. Whoops. Here we go. 0.707, da, 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 da. Okay? And there I have encoded all the information in the Library of Congress on one bar of impervium. It goes for a very high price because it's thermally very stable. And I will take it home with me. Now, what's wrong with this? Why doesn't this work? It should work, right? Little green man. Okay, so
There's a finite width.
let's say I encode a second thing saying how many bits there were.
There's a finite width to the line that you're scratching.
Finite width? Oh, that's not a problem, Sam. Look, I'll just say it's the left-hand side of the line that counts.
You're never going to get the resolution.
Ah, the resolution, right. Okay, so there are a finite number of molecules that make up this thing, and it's probably the case that we're going to run out of them trying to divide this down to that accurate of a number.
Also, as any physicist knows, there is no exact number.
There is no exact number, and there's also noise. Okay. This thing will stretch with heat back and forth, trying to read the thing. How am I going to read it? I need a ruler to somehow measure this thing by. The ruler needs to be good too, right? There's all kinds of issues trying to read this thing. How many bits do you think I can get scratching a line in a bar? Let's say that this was actually 1 inch long. Anybody here know enough about physical things to know how accurately I can make a bar that's on the order of 1 inch high? Can I make it 1,000th of an inch? That accurate? Anybody know? Someone must know this. Sure. Okay. That's called 1 mil. Okay, it's 1,000th of an inch. That's easy. So 1,000th. So a part in 1,000 is okay. How about a part in 10,000? Is that easy? Well, we also could figure that out too. But even before we get there, part in 10,000, yeah, we can make things that accurately. Part in 100,000, starting to get shaky, okay?
Depends what we consider easy, because
Part in 1,000,000,
molecular, we can do things down to molecular levels.
it is true.
Techniques.
It's true, but we have to depend, at the National Bureau of Standards, they have this, 1,000 gram weight on a piece of velvet, right? It's sitting there saying, this is 1,000 grams, period, okay? Well, not really, okay? It's 1,000 grams today, and tomorrow it's 1,000 plus a little bit, and the next day it's that minus a little bit, and every time you measure it, it's different. The velvet rubs off a little bit of the gold, which is what it's made out of, or I'm not even sure what it's made out of, but the stuff that it's made out of. A molecule adheres to the surface, goes away from the surface, all sorts of things. Turns out that with standard techniques, we can get around a part per million, so 1 in 10 to the 6th out of this thing. Okay? What's log base 2 of 1 in 10 to the 6th? So what did we say before? 10 bits is 1,000 roughly. So how many bits in a million? Around 20 bits. So we can store about 20 bits. And how many letters did we say that is? So there's 5 bits per letter. So we have 20 bits that we can store. So we can store it, space, W. That's as far as we're going to get in our quest to encode the Library of Congress by a scratch on a bar.
Intel making transistors like 3 atoms difference between them?
Oh, sure. But it's not that they're saying that they can tell the difference between a bar that's an inch long that has 3 atoms or that doesn't have 3 atoms. And what's necessary here is that I be able to measure an extremely small difference on top of a very big difference. And that's different than saying, if I only looked here, can I build a structure that's very tiny? Okay, that's not the same.
Oh, but they must have some superior way of measuring.
Okay, well, if,
The average human cell is about how
well, let's talk a little bit about that too. Okay. So let me get to that, Sam. Okay. So there is noise. There's noise of all sorts, of this thing growing and shrinking and getting rusted, all kinds of things. And in understanding a system like this, it's important to consider noise. And the other day we talked about the difference between an analog system with noise and a digital system with noise. And in general, what we're going to do is we're going to say, look, there's no way you can measure this thing perfectly. What I'm going to do instead is I'm going to divide this up into a number of sections, okay? And I'm going to say if the mark is in this section, in here, then that'll mean that it's data item number 1, 2, 3, 4. That's a choice of 1 out of 1, 2, 3, 4, 5, 6 possible places to go. And maybe I can be smart and divide this up into many things, but we just said you can't divide it up into more than 1 million ones because of the noise. And so over here I've drawn a picture of this, and basically the transmitter, out of a possible space to transmit, known by the symbol P, P stands for the power available to the transmitter, is picking a symbol to send, which is this line right here. The noise in the world, in the device itself, in the receiver, is going to expand that signal from that space P into some symbol within here. And this is the uncertainty of trying to measure that bar. Okay? And this is the noise N.
Are we limited to only sending one signal, though?
Well, we're only going to think about that
Only
right
one
now.
spot in one of those spots.
Terrific question. Okay, and the answer is if you send more than one, things get better. Okay? In fact, one of the things you might think about doing is sending 1 bit in each one of the places. And that would in many ways be the best use of the bar. Okay? But let's talk about just sending 1. Okay, the maximum number of symbols that we can send in this bar that's P long and that has a width of N, how many things can we divide up into this thing? Well, P over N. And so we have a choice any given time when we put a scratch in the bar of really only sending, if we're only going to put 1 scratch, log base 2 of P over N bits of information, which is that short calculation that I just did up there. I said the uncertainty is around 1/millionth of an inch. N is 1 millionth of an inch. The bar is around 1 inch long. And so log base 2 of 1 divided by 1 over 1,000,000 is log base 2 of 1,000,000, which is around 20 bits. Okay. This formula that's right here is the formula for channel capacity that Claude Shannon figured out. And what he figured out was that in general, if a transmitter has a power P, which is equivalent to how large of a space it has to pick from in sending a transmitted signal, this is the length of the bar, and the noise in the channel is N, then log base 2 of P over N is a measure of how many bits each symbol is going to actually say, how many bits you can send per symbol in the channel. Now, it turns out, of course, that if I'm sending bits down a channel, I may not just send 1. I typically send 1, and then I send another 1, and then I send another 1. And W is a measure of the bandwidth, how many symbols per second I'm going to send down the channel. So if I want to know how many bits per second I can send down a wire, this is the formula that I use to figure it out. Now, P is not measured in inches, N is not measured in inches. P is measured in actually watts of power, N is measured in watts of power that I send down the line. But it turns out that the analogy is actually true. It's the same as saying that I have a width that's this big and I'm scratching a line within that certain width. And the bandwidth W, I believe, is measured also in the number of symbols per second. Okay. In the case of an analog system, the formula is actually the same, but the definition of W, P, and N are slightly different. But then, anyway, this is a very famous formula, which is kind of good to know, and it's neat that if you think about it, you can actually understand where it is coming from.
You said in the case of the analog, it's different. What this is?
The meaning of each of these. This is sort of a discrete way of talking about this thing. So it's a discrete system, and anyway, if you look at that book, you'll see the whole thing. So anyway, here's the book that talks about it, and here's the other book that talks about how to deal with redundancy. Okay, so we have this idea that we can deal with noise by segmenting our input space into finite numbers of segments like this and transmitting a high-quality signal in there that may, because of noise, get contaminated up into a certain border over here. It turns out that when we're sending multiple bits of information from one place to the other, we have to think about something else which has to do with physics as well. And I hinted at this before when I talked about how the flip-flop worked. Remember that a memory system stored energy. It stored charge. And basically, in order to store a bit of information, you need to store energy. In order to transmit a bit of information from one place to the other, you need to transmit energy. And so you may look inside your computer and see wires all over the place. And you may think to yourself, I know how wires work, because wires, after all, are conductors of electricity. So it must be true that if I put a voltage here, V1, on this part of a wire, that voltage appears on V2 and also on V3, because the wire is made out of copper, after all. So is that actually true? Well, it turns out that it's only true if you look at it kind of slowly enough. In other words, if you don't care about the dynamics, about how fast things are taking place. What actually happens is when you put a voltage on a wire over here, it acts like a tightrope. Okay? And a wave occurs from this side of the wire to the other side of the wire as the information about the new voltage gets transmitted down the wire from one end to the other. Just like a rope that you shake a little bit, and that wave of information travels from one side to the other. So you may think of wires as having the same voltage throughout, but in fact it's not true. So let's take a little bit of a look as to why this is true. So again, I'm only going to give qualitative physics for poets kind of versions of this thing, but hopefully a little bit later you'll get to understand it a little better. It turns out that wires, all wires, have certain what are called parasitic characteristics to them. And one has to do with something called inductance. And this is modeled by this little coil-like thing here. Okay? And what it says is that the piece of wire doesn't like to have the current change in it very fast. Okay? It is lazy. Okay? And if you suddenly try to change the amount of current in a wire, it resists the change. It says, whoa, wait a minute. And it takes time to move it to allow the current to change. In the same way, it turns out that, and we've talked about capacitors just a little bit, there is capacitance between the wire and the rest of the world that also resists change, and that resists change in voltage as opposed to current. Again, this is sort of just speaking generally, and don't worry too much. Try to get the big picture of how this works. The resistance to the change in voltage that happens over here is because a capacitor kind of acts like a reservoir of charge, like a bathtub. And a bathtub, if you think about it, resists change in the level of the water. You turn on the faucet, and it's not true that instantaneously the level of the bathtub goes up, right? It takes time for it to go up. It resists the change, and so it takes time for it to fill. In the same way, currents traveling along a wire generate magnetic fields. Okay? And many of you, I think, know this. And those magnetic fields don't like to change either. And in order to change the magnetic field, that takes time too. And so we have resistance to change over here, resistance to change here, and the equations here, which Sam's son is going to talk about a little bit, are a description saying that the rate of change of the voltage in a capacitor is proportional to the current that you put into it. the same as saying that the rate of change of the level of a bathtub is proportional to how fast the water is going in. Okay, this is how fast the water goes in. This is the rate of change of the level of the bathtub. Okay, and this C is a measure of how big the tub is. Okay, the exact same sort of an equation holds for measuring the voltage and the change of current in a coil of wire or a piece of wire as well.
L is the inductance?
Yes. Yeah. Yeah.
So is the speed of information transfer different from the speed of the carrier, the charge carrier which is moving through the wire?
What's the right way to say that? The average speed of the carrier is, let's see how to say this the right way. The speed of the carrier through the wire, speed of the information through the wire. So I need to think about that a lot to get that right. I think in general you're right, but you need to be careful about this because first of all, the carriers themselves never are all moving in a straight line. Okay, some of them are moving backwards, some of them, so they're moving at random. So their speed, quote unquote, is different than their average sort of drift one way or the other. Second, the information can be sent down the wire by having the carrier go forward and then come back. And the information propagates down. I whip the clothesline like this, but it doesn't mean that my hand goes down the wire. And so, but for certain modes of signaling where you're applying a DC current going down the wire, then I believe you're right, that the speed of the charge carriers going down the wire is the same as the speed of the bit that's going down saying there is current. Okay, but that's not the usual case. It's usually more like this. You're going up and down. So there, the answer is no, that the carriers don't actually drift towards the end. But they change like this on this end, and that change propagates towards the other side.
But I thought the signal was the speed of light.
Ah.
Essentially, while the carriers were just like moving slowly and slowly.
But it's not true. Okay? So a radio wave will propagate in a vacuum at the speed of light. But an electrical signal will not go down a wire at the speed of light. If that wire is, as it typically is, in air, it'll go a little bit more slowly. If the wire is on a circuit board, it'll go even more slowly than that. And the reason is that the L and the C here are bigger than they are in free space in a vacuum.
It's the same order of magnitude, right?
The order of magnitude is roughly the same, sure. Sure.
While I guess the electrons are moving much more slower. They're not moving that order of magnitude.
Well, the electrons, so the question is, what does it mean for how fast they are moving? Okay. So, is it how they move at random? In that case, they're not really moving even. They're kind of jumping from one place to the other.
Both those speeds
So,
are bouncing as well, right?
it depends. So there's thermal speed. This is like a big ball of worms here, or can of worms, and I'm sort of a little reluctant to open it here because there's many different ways of talking about what the speeds are here. But anyway, what a transmission line actually looks like is a bunch of inductors and capacitors all the way down, okay? And the result of these elements is that it takes time for signals to propagate from one end to the other. The other part about this picture here is that inductors and capacitors store energy, okay, if you remember from your physics textbooks. And it's exactly the same as a bathtub full of water storing the potential energy of the water that's in it. And then when the water drains out, the energy is gone, okay? You can think of these as a series of bathtubs going along the line. And these is a series of pipes that don't want the flow in the water to change speed. Okay, the water wants to keep on going the same speed because there are a bunch of cars that don't want to change speed going down. There is energy in each one of these elements. And what it means is that if I'm over here at the transmitter and I send a signal down a wire over there to the receiver, the way that I do it is I inject energy into this transmission line. And the line takes that energy and propagates it like a wave going down towards the left-hand side and transfers it from this element to the next set, from this element to the next set, from this element to the next set, all the way to the end. Okay? It's exactly the same as when I'm talking to you. The way that that information is sent to you is that my vocal cords are doing this, right? The air gets compressed, and then a wave of compression leaves my mouth and heads towards your ears, and then hits your ear, and then your eardrum goes like this. Okay? In between the time when I say a word and when it gets to you, where is the word? The answer is it's sitting right here in the middle of the air. Right? How fast does sound move? Around a foot per millisecond, right? Okay, everybody has their own way, but around a foot in a thousandth of a second. Okay? So after a few thousandths of a second out here, but before you hear me, the energy is sitting right here in the air. In what form? The air is squeezed a little bit. Not very much, but just a little bit. And then it keeps going out to you, okay? And that's an amazing thing, because what it means is, first of all, things take time to get to you, because there's a finite speed of propagation of this squeezed air, of the energy transferring from one to the other. And the other amazing thing is that when my sound gets to you, you have to do something with the energy. Okay, you suddenly receive the energy that is propagated along the line, and you have to get rid of it. And the answer is, where does it go? And believe it or not, it goes into heating up your clothes, okay, and heating up all the things in this room here. It doesn't heat up the walls very much because they're very hard, and sound tends to bounce off of the walls. But when it gets into our clothes, there's so many paths for the sound to bounce off of that it just ends up turning into heat in our clothes. So I'm making all of you warm by talking, okay, hopefully. But if it doesn't have anywhere to go, then it echoes. And of course, all of you have done this with sound in the past, right? You go to a place with a hard wall and you talk to it, and it echoes back, and it can go back and forth a few times. It turns out that in computer design, this echoing is actually a problem. And I'm not going to bother to go through this now, but you'll see it later. But what this all turns into is a result showing that there is a certain speed to the propagation on the line having to do with L and C. And there's something called the characteristic impedance of the line, which is a relationship between the voltage and the current as you go down the line. And again, I'm going to pass this all off to Sam's son to do. What you are going to learn now is that you have to do something with the energy when it gets to the end. Okay? And the way that you're going to dissipate that energy, if it's an electrical signal, is you will dissipate it in a component called a resistor. And a resistor is something that resists current and dissipates power. Every light bulb, for instance, any of the old style light bulbs, is nothing more than a resistor which gets very hot as a result of the current that is going through it. And so in computers, how many people have bought terminators for the SCSI bus in their Macintosh or something like that? Do you know what's in those things? Yeah, see? This is magic. Well, it's not magic anymore, okay? What's in the terminators for the SCSI bus are a bunch of resistors, one for each of the data lines that's in there. And where do you put the terminators? You put them at the end of the chain. And the reason is that when the computer sends a signal out on the bus towards the receiver, if it doesn't want the echo to come back to it, it needs to dissipate the energy. And so believe it or not, the terminators that you put there at the end, when data is being sent, they heat up just a little bit with the data that's being sent towards the other end of the line. And in computer design in general, particularly when you're dealing with high speed, you're going to discover that you're going to need to put terminators like this all of the time. And so modern computers have many more terminators than older ones have. And why should that be? Well, if I want to get around echo, let's say I'm in a room with a lot of echo, what do? I talk really slowly, because in between each syllable that I say, the echoes have time to die out. And so they don't end up clobbering the future things that I say. If I want to run a computer slowly without terminators, all I need to do is change between 0 and 1 very slowly. The echoes still happen, but they happen in a time that's short compared to the time of the transitions between zeros and ones. So if I don't want to send signals too rapidly in the system, the need for terminators is much less. Okay? Another way of thinking about it is if you take a clothes rope, right, and you slowly move it up and down like this with your hand, do you get waves that propagate down? You just slowly go up and down like this. No. If you want to get a wave to go down, you kind of snap it. Bang, 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 like that. Because if you move it slowly, what actually takes place is that the wave actually does go back and forth, but it goes back and then forth, and you're still pretty much where you used to be, so you don't even see the wave. Okay? And then you slowly are moving up and down. On the other hand, if you're trying to send data very fast, then you begin to see this thing. If you put the end of the rope in some viscous fluid, which would absorb the energy of the whipping, the waves would only go down one way and they wouldn't echo back. Okay? But if you don't, if you tie them to a hard wall and you go like this, the wave hits the end and then it echoes back to you. There are many ways to do this resistor. One is in parallel like this. Another way to do it, it turns out, is to put the resistor in series with the source. I'm going to also leave that to Sam Sun. And there's a discussion which he'll get into as to why you would choose one versus the other. Okay? This doesn't really make much of a difference for what you're trying to get right now, which is this fundamental idea that sending information equals sending energy. And if you're going to send it, you've got to have somewhere to put it at the end. In general, this rule as to when you need to worry about termination and when you don't has to do with what the time delay, the time of flight between the transmitter and the receiver is, and what the rise time of the signal is compared to that time of flight. So it's again the example of the clothesline rope. If the rise time, how fast you raise the rope up, is less than 2.5 times the time of flight between one end of the rope and the other, in other words, it's slow compared to how long it takes for the wave to get there, then you don't have to, oh, I'm sorry, I'm saying this wrong. If the rise time is less than 2.5 times the length of the rope, then you do need a terminator on the other side because you'll get waves. On the other hand, if the rise time is more than 5 times the time of flight, in other words, you're going to go up so slowly that the wave will have a chance to go back and forth 5 times before it gets to you, then in general you do not need it. And this is very typical of computers built in the 1970s, and this is much more typical of systems that are built now.
Time of flight round trip?
Yeah.
Time of flight in this case is not round trip. It's from one end to the other. Yeah. We're actually more worried, yeah, that's an excellent question. But that's just from one to the other. Yeah?
Why is termination different than ground?
Well, here's the trouble with ground. So how do I explain this without getting into the math here? Okay. Let's say, how many people here know how an organ pipe works? Anybody? Yeah. Okay, it's great, right? There's this, thing at the, sort of like a Coke can. Everything's like a Coke can, right? So there's this mouth. Here, I'll draw it on the wall here. I can get this right here. It's sort of like that. I'm doing this a little bit wrong, but anyway, the air goes in here, right? And the air goes in here, and the air begins to flutter back and forth across the mouth of the thing. And sometimes the air goes out like this, and sometimes the air goes out like that, okay? Yeah, it's just sort of like, our lips when we blow across the top of a bottle. Some of the time the air goes straight, some of the time the air goes in. And it flutters back and forth. And as a result, if I didn't have anything higher than the pipe, I would get this fluttering, but kind of like white noise, sort of flutter back and forth every once in a while. But what actually takes place is that a flutter propagates down this pipe exactly like the signal going down a transmission line or a wave going down a rope. And then traveling down this line, and it turns out the molecules have mass to them, which means they don't want to stop when they're moving. Sounds just like what we were talking about. A wire, the current doesn't want to stop, okay? And the volume here of air says it takes air going in for a while before the pressure will change. The pressure doesn't want to change either. So the velocity doesn't want to change and the pressure doesn't want to change. And the result of that is that you get waves that propagate down this tube, okay? They finally get to the end, okay? And when they get to the end, if the tube looks just like this, they will pop out, and all of a sudden they go out into the big wide world where the pressure is the same. and the velocity is 0, okay? Or actually, it's not quite 0, but they can go out and have speed when they go out. What happens when the wave goes out here and there's nothing at all here is that a new wave is created that bounces back. It's what's called an open circuit, okay? Goes out and then all of a sudden, pop, there's nothing there. And a new wave begins to propagate down that is the negative of this wave here. And that propagates until it reaches the lip here. And it turns out that the wave that propagates back sort of takes some time to get back. And if everything's working out right, this wave going back exactly reinforces the wave going up, so that by the time it arrives, this guy is generating a new wave that's exactly in phase with this, and that determines the tone that you get out of here.
So these
Okay.
waves are all in the air, they're not in the actual metal of the pipe?
They're in the air. The metal of the pipe, it changes the quote-unquote, sound a little bit. Okay, like metal pipes sound a little different than wooden pipes and stuff like that. And there's all different kinds, and there's certain types of metal that are used.
What causes this echoing wave?
What causes it is the discontinuity at the end. Okay? It would be easy for me to explain this, and you would all believe it if I said that we close off the end of the pipe.
Right.
You would all buy that, right? You'd say, okay, the wave bounces back. It hits here, and then a positive wave, this one's going this way, then a positive wave looking just like it comes back. And if it comes back and hits this guy just at the same time that he's generating the next cycle for the next wave, exactly in phase, then you'll get what's called a standing wave in the pipe, and that'll give you the tone that you're meant to get. Okay? But it turns out that if I open the end of the pipe, I also get a wave that comes back, but it's a negative wave. Okay, so let's see, I need to bring in a little organ pipe to do this. The flute works exactly the same way, right. Now if you close the end of a flute, what's the sound versus if you open the end? It sounds dead. Well, then it's, yeah, okay.
Well, what was the answer?
You can do it, and it's a slower
Well, it's
frequency.
because the flute, if you plug into the flute and you put all of the keys down,
All the key, there we
I
go.
can't predict what that would do, but all the keys.
Okay, so I'm going to bring in a little organ pipe to our next, I don't know if I can get it in time for our next class, but I'll bring in a system or a piece of plastic pipe and we'll do this thing, okay? And what you'll discover is that one of them is half the frequency of the other. And it has to do with whether the wave that comes back is positive or negative, okay?
Yes, you're
When
right.
it reinforces the other one. So one is an octave different than the other one.
On the flute, you're playing in the bass tone, you're playing on several harmonics at the same time, and you lose
Right.
the upper harmonics when you close the end and all the keys are down.
Okay, right. So in general, closed pipes, I believe, are lower than open pipes. And so anyway. The effect here is the same. If we either do not connect the wire at the end, or if we connect it to ground, we get a reflection. Okay? And it's hard to believe this, but if you're in a canyon, right, and you yell down the long way of the canyon, and at the end, the canyon opens up into nothing, and let's say there's a ceiling to the canyon. Okay, lots of ifs here. Okay? You'll actually get an echo off of the discontinuity off the end of the canyon where the canyon opens to the wide, wide world. Okay, as suddenly this traveling wave is going pop, a negative wave will come back. Okay. Okay. Yep. The other thing is, of course, if you put a wall at the end of the canyon, then a positive wave will come back. And so, anyway, this is really cool stuff. But this in itself is a 4-week course in physics to teach about waves and all that. So I can't quite go into all. Well, your son is going to do it all. So. Okay.
He speaks very clearly.
One of the things that your son is not going to do, and which I will completely brush over here, is how wires act on circuit boards. You guys don't need to know this at all, because by the time you're out there doing these things, who knows? We may not use circuit boards, and we'll use something different, or we'll build things out of I don't know, Jello or something. But the technology that we use these days is copper wires like this on top of what's called a ground plane, which looks like this, which is also copper, and it's insulated by fiberglass typically. Okay, and it turns out that if you care about these things, the equations for exactly figuring out what the capacitance and the inductance of wires that are set up like this are given in the next slide, which you can barely even read, but they have to do with how wide the wire is, what the height of the insulator is, and sometimes we actually even bury the wire in between, inside of an insulator like so, in between two ground planes like this. It's called strip line as opposed to micro strip line. All that matters is what the final answer is, which is that typically the speed of propagation of wires on a circuit board that are inside of your PC is 1.4 times 10 to the 10th centimeters per second, or 14 centimeters per nanosecond. So who remembers the speed of light, since you asked about the speed of light?
300 million meters per.
All right, so this is somewhere between 2 and 3 times less than the speed of light. So between a half and a third of the speed of light. Okay, so do not believe anybody that tells you that the signals in your computer are moving around at the speed of light, because they aren't. They're moving around at a fraction of that. If the wires were out in space and the wires were very, very thin, then it would be at the speed of light, but they aren't. Okay? It's because the capacitance of the circuit boards is more than free space is, and the inductance of the wires is also more. The resistance to change is greater, so it takes longer for the signals to propagate. Okay, I think that's probably it.